Hello. Today we're going to be talking about orbital approximation and Pauli's exclusion principle. Okay, starting off, the orbital approximation. You have a proton and an electron. You have a wave function that represents this. And if you operate, whoops, fancy H, if you operate on that wave function by the Hamiltonian, you get the energy. Broken record. So this wave function is both a radial component and an angular component, where the radial is both dependent on, it yields the n and l values, and the spherical harmonic depends on L and M sub L. And I shouldn't say depends on, the outcome of determining which of these two satisfy the Schrodinger equation gives us n, L, M sub L. Cool. For one electron. We know what this is for the hydrogenic atom, which is one electron and Z protons. Cool? Okay, so how often do you just have one electron? Very rarely. So when you want to include multiple electrons, the way you do that is the orbital approximation. You've all heard that so this is called the periodic table. Sorry. So the hydrogen is the only one we've actually solved. What does that mean? Where are the electrons and what is their energy? Where are they? The probability distribution psi squared, integrated over the entire space of where the electron could exist, and what is their energy? The solution to the Schrodinger equation. So that's only been solved for hydrogen. Everything else, helium and lithium, they all require an approximation. This is one of the approximations. There's a couple others, and the more complicated the atoms get, the more approximations you build. And that's where you're going to see I've totally blanked on it. It's later in the section. Oh my gosh, I'm going to keep, it's some sort of field. Where the hell is it? It obviously doesn't matter, but it's the last section. Whatever, I'm going to stop. Orbital approximation. We'll start with what that is. Okay, so we have, so this is equal to psi. Okay, so if I have psi, which is my total wave function for electron 1, I'm going to say that is going to be electron 1 at R1. Okay, but there's also going to be, whoops, electron 2 at some R2. But then there's also going to be some electron 3 at R3, and so on. Okay, so this is the total wave function that has multiple R's, for one R for every electron. And then for every R, there's going to be a theta and a phi associated with its colatitude and azimuthal. Okay, so how do we then represent this? Well, we represent this as the wave function. I'm going to represent this as a phi. I think that's Atkins notation. It can be a phi or a psi, either or. As the R1 phi multiplied by R2 multiplied by the wave function for R3 multiplied by the wave function for the number of electrons that you have Rn. Hi, kitty kitty. So this represents the hydrogenic atom wave function that you would have here. So this is R1 spherical harmonic. This one is R2 spherical harmonic. This one is R3. Da, 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 da. Look how big this gets. So cool. So you've got, think about now, if n equals, I don't know, 2, L equals 1, M sub L equals +1. For this one, now imagine what the total wave function psi would equal for a multi-electron system. It's getting pretty damn big. It's so cool. Anyway, cool. So this is called the orbital approximation. Is this right here, where you multiply hydrogenic atom that we've done thus far 1 Same thing, now you just multiply them together. And what they do is they end up giving you, when you put this into the Schrodinger equation, they give you the energies for the different electronic states. Cool? Orbital approximation. This is what we will need to solve multi-electron systems. All right.